So I'm totally excited about programming with Python, doing math with NumPy, and putting all of that together to do something really cool, which is make an audio synthesizer. But before I start talking about all the things like AM and FM and ADSR and things like that, let's just do something simple to start. And that is make a simple sine wave using NumPy and Python. So with that, let's get started. Alright, so we're going to make our first sine wave with NumPy. And so, let me have you hear what it's going to sound like when we're done. And we're going to do it with this code. So, let's dive in deeper and learn what each of these lines does in order to make our sine wave. Because this is the very most fundamental building block of how we're going to build audio synthesis. In this screencast, we're going to create our first sine wave using Python and NumPy. And this is a good starting point because the sine wave is the simplest type of waveform we can make. So first of all, I want to create a sine wave. That's the first big objective. And the next one is store it in a wave file for playback later. So the concepts I'm going to have are that of basic signal processing, such as sampling, samples per second, bits per sample. I explained these in another video as well, if you need to review that. And then I'm going to be using some Python development techniques, as well as showing how NumPy especially works to do high-performance mathematics on long sequences of numbers. NumPy is really the secret sauce and the magic behind what we're doing here. So for the tools, I'm going to use Atom, and that's for text editing. I'm going to use the Anaconda Distribution of Python 3, and this has the advantage of including NumPy and SciPy pre-installed, so I don't need to install other software with it. And if you continue going on with other things in Python, it has so much more. I highly recommend it. I'm going to demo this on Mac OS. However, it could be adapted to Windows or Linux, though I won't show that. But basically, if you have the ability to write a Python script and run it, and then play a WAV file, you could do this on the operating system of your choice. And I will also use Audacity, the free audio editing software, to show results and what the waveform looks like. So without further delay, let's get going. So here's how to get the various pieces of software that I mentioned we'll be using. The first one is atom.io. And so you can download that for a variety of platforms. It shows download for Mac because I'm on a Mac system here. The next thing that you can get is the Anaconda Distribution of Python and a bunch of other interesting things. I'm using Python 3.6 version, and that's what the demos will be in. And then depending on your operating system and preferences for how you install, get the command line or graphical installer. Just make sure you don't get the Python 2.7 version. If there's things in the demo that depend on having a graphically installed Anaconda distribution, you won't see them using it because I'm using the command line installed version. And the Anaconda official installation instructions contain much more detail on how to install these programs with Anaconda. Now, if you want to completely roll your own, and you already have a Python installation you don't want to mess with, then you can feel free to install NumPy, which is at numpy.org separately, as well as SciPy at scipy.org as well. I won't cover the installation specifics of any of these pieces of software because they will be different for each of your systems. However, what I will do is in the show notes also link to these websites on where to get these pieces of software. So on my desktop, I've created the beep beep directory, and that's going to hold the script and its resulting output. And then I also have a terminal window opened up to it, and that's how I'm going to execute from the command line the Python interpreter that actually will run our script. And then lastly, I have Atom opened up in that directory so that I can make the file that we're going to run as a Python script. And as you can notice here, we have the get directory, the waveform demo data, the waveform demo AUP, and the .gitignore. You won't necessarily see these on your computer unless you go ahead and do Audacity in the same directory like I'm doing, and you do a Git repository as I am doing. But we're going to go ahead and just put the Python in this beep beep directory. So what we're also going to need to do is ensure that we're using the right version of Python. So I'm going to go over to the terminal where I'll be running this. I'm going to type Python to get to the actual command line interpreter. You can see we're using Python 3.6.0 out of Anaconda 4.3.1. So that means that we are ready to go. And so let's go over here to the Atom text editor and do just that. I'm going to create a new file called firstsinewave.py. And then after that, the next thing we need to do is import numpy as np, which will give us the numpy library to do the calculations with. And then from scipy.io wave file, I'm going to import write, which will allow us to write the wave file to the disk. And so now we're going to set up a few variables to help us along our process. So the first thing is going to be the samples per second of our waveform. We call SPS. And it's going to be 44,100 samples per second. And so where did I get this number from? So if we go over to the web page for compact disc digital audio, we can find out more about where I'm getting this sample rate from. So if you see over here, it says in the CD audio format, it is 2 channels of Sine 16-bit values sampled at 44,100 hertz. And so basically, without going too much into signal processing theory, that allows you to capture what the human ear can hear for sound. There are, of course, higher sampling rates that give you more audio quality, but we don't need those for our application right now. All right, so now that we know why we have our samples per second, we're going to make the frequency, so the pitch. I can't spell. So it's going to be 440 hertz. And notice how I'm keeping the unit with the actual variable name so that if I ever have to debug it or look at my code for any other reason, again, I know what the units of these are. And we're going to have a duration. I'm going to say the duration in seconds is going to be equal to 5.0 seconds. So we defined our samples per second, 44,100, our frequency that we're going to be outputting a sine wave as 440 hertz, and our duration that means we're going to make a sine wave of length 5 seconds. This is my favorite part of the script. In fact, so favorite, I'm just going to call it the NumPy magic section. And so if you recall, that NumPy actually does things very specially. It operates on something called NumPy array, so we're not in the world of Python lists anymore. And NumPy arrays know how to run very quickly, as opposed to, say, taking a Python list and going over one at a time with a for loop. A NumPy array can be calculated several values at once, which greatly speeds up its performance. And since it also only holds one data type, that means that it gets that much more performance boost. So it takes from what would otherwise be the slow Python language and drops into the faster C language to run the calculations for us. So how does this work? So recall Python's range function that will give us a Python list of numbers that we specify. NumPy has a similar function that makes a NumPy array, and it's called NumPy arange. So I need it to give a sample number for every sample we're going to have in our wave file. So that's going to be the duration in seconds times the samples per second, what does that come to if we plug it into the calculator? So the duration in seconds is 5.0, and it's going to be 44,100 samples per second, which is about 221,000 samples, or 220,500 to be exact. Now that we have each sample number that we need to record in our waveform, we can let NumPy calculate our sine wave for us. And once again, this is some NumPy magic. So rather than using a for loop, I'm just going to use one line, and NumPy is going to know how to calculate the whole sine waveform. Now I'm about to use an equation that I explained in the basics of signal processing video, but for now, just trust me on this. Waveform is equal to np.sin of 2 times np.pi times each sample number times the frequency in hertz divided by the samples per second. Now there's two interesting things here at work. And the first one is that NumPy can take a simple arithmetic operation, and if you just give it to a NumPy array, it can do what's called broadcasting. In other words, it takes that arithmetic operation and then makes another array that has that operation done across it. Now, why does that concern us? Is if we remember that we can multiply our sine wave by a number and get an amplitude for it, that means that we can make it louder or quieter. And as it turns out right now, this waveform is as loud as it's going to get. So the waveform is a series of floating point values between negative 1.0 and positive 1.0. And we need to make sure that it does not go to the edges of that value. And why is that? Because, as you will find when you're making new synthesized sounds, is that it's very easy to make things that are very loud. And you might not want that. So I'm going to go ahead and make a quieter version, so it's called attenuation. I'm going to call it quiet. That's going to be a result of waveform times 0.3. So that will put everything from the max value of positive 1 or negative 1 to the max value of positive 0.3 and negative 0.3. Now that we have the quieter version of the waveform in hand, we still have floating point values. We need to convert it to integer values. And why is that? Because if we recall our CD audio format, we have signed 16-bit values. And so having signed 16-bit integer means that we're going to go from negative 32,767 to positive 32,767. So we need to tell two things. NumPy, you need to make an integer array, and NumPy, put it between these values. And NumPy also uses this many bits per sample. So luckily, that is fairly easy to accomplish. So I'm going to make another value here called waveform integers. It's going to be np_int16. So that tells NumPy, okay, I'm going to give you a set of values. I need you to make a 16-bit integer array out of it. And that's going to be from waveform quiet, which we've attenuated, so it will sound just a bit softer. And we're going to multiply that times 32,767 for each sample, so we get that range that we need. And finally, last but certainly not least, we will type in right. We're going to call it first sine wave.wave, samples per second, and waveform integers. So this goes up and tells the write function that we imported out of scipy.io wave file to write the file first sine wave.wave at 44,100 bits per second and take that out of the NumPy array waveform integers. And so that is how we have transformed this list of the frequency and the duration that we need for our sine wave into something that's a wave file that we can play. So now we have the moment of truth. We're going to write our first sine wave and play it back. So I am going to make sure with Command S that my file is saved. Then I'm going to go over to the terminal. And so we see a few files here in our beep beep directory. Waveform demo.aup and waveform demo data are just Audacity files. I'm going to use that to show you what the actual waveform we made looks like in just a few minutes. However, the one we're really interested in is first sinewave.py. So, number one, before I forget, I'm going to turn my sound all the way down. I'm going to then run Python first sinewave.py. Now think here for a moment, and there we go. So let's go ahead and open up this directory in our Finder and take a look here. Now, as you recall, I turned my sound all the way down because this could be loud. So I'm going to run it. I have here in the audio player. And so that is our first sine wave. As you could notice that I start out the first time by turning the volume all the way down and then turning it up until it actually became to an audible level. And as you noticed, it only took two volume marks going up to get something that was fairly loud, at least here in the studio. And so that is why, one, I turned the volume all the way down before I played it, and two, in the actual software, I attenuated it down to 0.3 of its max before I played it. So let's just review what we did here. And so the first thing is we went and got the NumPy library, and then we used the SciPy wavefile writer. We defined how many samples per second we wanted our waveform to be. We defined how the frequency in hertz we want our waveform to be, as well as its duration. We then calculated a range of sample numbers as a NumPy array, not a Python list, to match each sample number we needed in the output file. We then calculated with the mpsyn function every sample number that we're going to use in the output. We then attenuated those samples so that they would be just a little bit quieter, because sound synthesis can get very loud. We turned all those quiet integers into, all those quiet floating point values into 16-bit signed integers to be part of the wave file format. And then we wrote out our sine wave to the wave file at a certain number of samples per second. So let's look at this visually to see what we have done with this waveform. It's just going to be a sine wave, but it will actually pull, I think, what we've heard, what we've done in code, and then tie it together with what we can see about sound. So let's switch over to Audacity. And if you recall, Audacity starts up with a project. It is not the same as the audio files that we're putting in. So I'm going to have to import our audio file. So import audio. And it is going to be our first sine wave there. I'll go ahead and make a copy of it. All right, let me make it a bit bigger. So here it is. We can start to see some sine-like qualities, but not very much until we start zooming in. There we are. And so this is our waveform. Going from our seconds of 0.004 to 0.006, we have that cycle and so on. And then we can also tell what is our max here. Our max is 0.3. So what Audacity just did is it took our integers that we had in the wave file and converted them back into floating point as it's going to be editing. So we can very clearly see what we did. So that is the result of all our calculations right here. So congratulations, you made and played your first synthesized waveform as calculated from raw math. That is quite an accomplishment. You did not use any external third-party libraries to do this. You just made the computer write out all the numbers that you needed. So that took some knowledge of basic signal processing, some knowledge of the math that goes on, some knowledge of how to efficiently do this inside a computer. And so excellent work, great job. And I can't wait to show you even more.